on the multiple choice questions, and this probably wasn't your best effort. By the time we take the next test on Wednesday, you'll be fine. Everything will be fine. I'm not worried about anybody in here. Just make sure you don't let your, you don't get lulled into a sense of complacency. Come on in. And don't get the homework done. I haven't checked Wiley Plus in a while because I don't like going to that website as much as you guys do. So I haven't seen what you all have done recently. So let me pass back the test to those who've just arrived. And then we'll get started today. And I thought I'd get started on relativity today, maybe, but I didn't because there's so much cool stuff. Even though I kind of stopped the problems. Is that on? I can't tell if it's on.
No, it's not.
It's not on. Come on. There we go. All right. Because I stopped the problems on the bragging hunter on chapter 27, but we're going to go over. Yeah. Let's see. Brenda. There you go. Who else oh, Kurt. There we go. All right. Okay, now, let me kill the lights here. Boom. Whoops. Whoops, that's probably too much. All right, now. Okay. Are you keeping up with me there? Going back and forth? Yes. Yeah. Sorry, I'll get situated now. I'm going to be over here. I know Dr. Roble wants me to use the gyro mouse, but I hate the gyro mouse with every fiber of my being, so I won't use that little pointy thing. Can't stand that thing. All right. But we are going to go here, so let's start from the current slide. Okay. The Mickelson Interferometer. It's a way of measuring the wavelength of light. Okay? And the way it works is basically we learned all about, and we'll do one problem at the end of the hour on that thin film stuff again. But anyway, basically what you're doing is if you keep moving this mirror a little bit, you wind up getting different diffraction gradients. Basically what it does is interference between two light waves. This thing splits a light wave. Basically what it does is it splits a light wave, okay? And then one reflects off a stationary mirror, the other bounces off a movable mirror and reflects from it and returns. And then when you combine the two together, the interference is observed. The amount depends on the travel distances, and then the wavelength of the light can be measured. So basically what you're going to be doing is you're going to be changing this distance dA. You'll be moving it back and forth, up and down, getting light. You can either see it bright, or dark. And depending upon where that mirror is positioned, you can measure the wavelength. Okay? So that's this way that Mickelson Interferometer works. Okay? But, and all of this basically boils down to all the stuff we're going to talk about today. And it's all pretty cool stuff because I did actually get into the CDs, how CDs and DVDs work and stuff like that. It all boils down to that light diffracts, okay? There's diffraction, the Huygens principle here, where every point on the wave front acts as a source of tiny wavelets as it's moving through. But basically all this means is light diffracts, so therefore it acts like a wave, and so therefore it bends around things a little bit, okay? Because its wavelength is so short, though, because its wavelength, especially a visible light, the wavelength for visible light is between 380 and 750 nanometers. Because it's so short, it doesn't bend a whole lot. It definitely doesn't bend like big old long, 1,000-meter long radio waves and things like that. But it does bend a little bit. All right? So it diffracts. Okay? Now, there you go. Here's water. We're showing water. Okay? Now then, there's water. Trying to figure out what I'm trying to conceptualize what they're trying to say. All right, here's the deal. Basically, it boils down to this. You got your wavelength, lambda, and the width of the slit that it's going through. All right? And the width of the slit. Okay? So if my width is big, in other words, lambda is going to stay about the same size. They got lambda about the same size in these two water waves here a little bit. But as my width gets bigger and bigger, the diffraction gets less and less and less. All right? And that makes sense to us. Because if I shoot a bunch of water out that door and it's wide open, then the water pretty much stays in its same path as it's going out like this. If I shoot a big bucket of water out this door and it's just going through that small little window opening, it's going to spread out when it gets through that small slit window opening much greater than if it just goes out through the open door. That's what they're saying. All right? Just those intuitive things that you already know. Yes, it's actually been done by experiment, and this is the way we do diffraction of light. Okay? So it depends on the size of the slit. All right? The size of the slit. Okay. If light behaved as Newton thought it did, in these little wave packets, he was actually kind of right. He didn't say wave packets, but he thought they're like little energy, little balls of energy or something like that. Light would look like this. But since it's a wave, it spreads out like this, and you get the dark fringes due to interference of the different waves, and you get the bright fringes due to that they're coherent. Okay? They're not coherent. Because of constructive interference. Sorry, I lost my mind there for a minute. Kind of out of it here a little bit. So let's start over. Destructive interference means we got the dark fringe. Constructive interference means we got the bright fringe. And this is for a single slit. This is for a single slit diffraction. Okay? So for single slit diffraction, basically, they're explaining why all this works. But anyway, here it is. For dark fringes, for a single slit diffraction. In other words, right here at this dark fringe, right here, and it's going to equal the sine theta. Okay? In other words, this is shooting across here. The angle that this opens up between these two dark fringes here is determined by m divided by the wavelength divided by the width of the aperture. Okay? And we're going to use this for the way we focus on things, the resolving power. This goes straight to our resolving power. All right? So they have a little question. Which is going to have a more diffraction? A wavelength of violet light, which is 750, say, nanometers, or red light, which is about 380 nanometers, if they're going through the same width. Which one's going to have a wider slit or a bigger angle? If red light is 380, purple light is 750, and we're going through the same W, which one's going to have a bigger angle? Violet, right, because you put the 750 in the numerator and divide by the same denominators, you do the 380, you get a bigger number. Okay? So it's going to diffract more. All right? It's going to diffract more.
I have a question.
Yeah.
Doesn't it matter what Like if we polarize light and then put it through a slit at different angles, wouldn't it matter what? I'm just trying to ask if you have the wavelength going through the slit where it doesn't bend around the corner. Like if you...
Well, if you have coherent, well, yeah, if it's not going to go through the slit at all if it's parallel to it,
because the
right?
The picture of water you showed has the wavelength is going like vertical and then the slit is horizontal.
Uh-huh.
But it's still bent around the corner. Because water, I mean, so that doesn't make sense to me.
Oh.
You see what I'm saying?
Well, okay, here's the deal. Let's go back here. It doesn't matter. In other words, if I have a light wave coming in like this, is that what you're saying? Then all of a sudden it may not diffract. It's still going to diffract because that energy that's going off this way is going to diffract through there.
But isn't the part of the wavelength that goes around the corner, isn't that what is causing it to bend around the slit?
Well, it's just because it's a wave. Yeah, it's bending around this. I don't know what you're asking really.
That's right. I'll try to formulate it now.
Okay, all right. Because if there's any kind of light that's coming this way, it's going in a wave, right? And so any portion of it is going to diffract, all right? The only portion that's not going to diffract at all is if I shine a beam this way. And it's going, oh, there's no light there. Nothing's diffracted. Okay. All right. Okay. So anyway, there we go. Now, this is what I was talking about earlier. This is kind of a strange thing. If you have light here, you put an opaque disc here, it looks like one of those magnets that we use. This is what shows up on the screen. You've got light and bright fringes, but you got that bright fringe right in the middle. This is always kind of, if you're playing around with a flashlight or something like that, and you put a nickel or a quarter right in front of the lens or something, you get actually a bright spot right in the middle, and you would think, if light behaved like a particle, completely like a particle, that what you would get is you'd get a dark fringe there. But no, it bends around this thing and causes a bright fringe right there. Okay. It all has to do with diffraction. Now, resolving power. Okay? Here we are with resolving power. When we're far away, I don't know, this bothers me because they put this thing in reverse order for the way I learned it. Okay, now, if you're far away, it looks like one headlight coming at you, right? As it gets closer and closer, we're starting to see two headlights, and then pretty soon we can definitely distinguish between two headlights. Now, resolving power is the ability for something like that. In other words, let's read what resolving power is. Sorry about that. Maybe if I get on the right chapter, I can actually read what resolving power is. Basically, here's the deal. I got this diffraction right here, okay? It's going through this circular aperture right here, all right? Okay? And the resolving power of it is how bright this fringe is, okay? How much it can take in, the differences that it can make between two objects. In fact, let me read it to you, because I got into trouble here. But the resolving power of an optical instrument, such as a camera, is its ability to distinguish between two closely spaced objects. All right? Okay? Now, so this is the wavelength. This is what is known as Raleigh's number, okay, based on a physicist, Raleigh. All right? And D is the diameter of the hole, which could be the opening in your eye, could be the aperture in a camera, those types of things. Its ability to distinguish between two objects. Okay? All right. Here's the camera aperture, object 1, object 2, and here's the exposure on the film. So it definitely resolves those two objects clearly. Okay? Oh, let's go back to that equation. Let's go back to that equation. Notice, the bigger the aperture, the bigger d, the smaller the angle. In other words, the closer in two objects can be next to each other so that, and you can still tell them apart, the bigger the d. All right? So, eagles, which we'll do this problem here in a minute, eagles have a real big d in their eyeball. The diameter of their eyeball of the opening in their eye is much bigger than that of human beings. So that they can distinguish between two things very easily, almost 3 times greater than we can. Okay? All right. But anyway, the Rayleigh criterion, that gives us this minimum angle of 1.22 to distinguish between two things. Now, 2 points, objects are just resolved when the first dark fringe of one is right at the bright fringe of the other. Okay? So, these two things are are just resolved right here. You got here's the intensity of this one, but its dark fringe starts right here. Its first dark fringe is right here, right where the main intensity of that one starts. Okay? So they're just resolved. Now, if they get any closer together, then I can't tell them apart. All right? Now, this is kind of cool. I'm going to turn off this thing real quick here. We'll go back to it here in a minute. But anyway, let's take a look at what this means. Let me do some figuring here. And this part's kind of cool. Then we'll actually look at that eagle. And human being. And then it's just like the Hunter problem that I gave you in your homework. Okay, now, here's the example of the Hubble spacecraft. All right, so the minimum angle, theta, and we can do this minimum angle like this. We don't need to do the sine or anything like that. Is about equal to 1.22, the wavelength divided by d. Okay, the wavelength divided by the aperture. Okay, so let's take a look at the Hubble spacecraft. All right, Hubble Telescope. All right, it's got a big mirror on there that reflects ultraviolet light that has a diameter of 2.4 meters. That's a big mirror. That's about 7 feet across. Okay, it's probably heavy too. Big heavy mirror. All right, and ultraviolet light, lambda, is about equal to right around, it's a little bit more, so it's about, let's say 200 times 10 to the negative 7 meters. Okay? All right. So I went and looked that up. And then what they're saying is, for the Hubble telescope, for Hubble, this is what they're saying, that the theta min is equal to 1 times 10 to the negative 7 radians. All right? So, what does that mean? Basically, it means this. I got two objects here, and the angle that this makes, is equal to that theta min. All right? So, let's say we've got two candle flames. Two candle flames that are 1 centimeter apart. 0.01 meters apart. Okay? Now then, here's the deal. You take this, and you go, oh, okay. This is pretty much a 90-degree angle. That's pretty much a 90-degree angle. These two r's are pretty much the same. So we can do it this way. We can say, all right, the tangent of theta min, and if theta min is less than 1 degree, then the tangent of theta min basically equals the minimum angle, all right, which is equal to 0.01 meters over r. So in this case, we've got 1.0 times 10 to the negative 7 radians is equal to 0.01 meters over r. And if I figure out what r is, r comes out to be this. R equals about 100,000 meters. Okay? Which is 10,000 meters is 6.2 miles. So 100,000 meters is about 62 miles. So the Hubble Space Telescope is so strong that it can tell the difference between two candles from here that are burning in Sedalia, roughly. Pretty amazing. That's what that means. So now let's look at the eagle flying. Or we've got a, I like this resolving power stuff in case you didn't notice. But anyway, let's take a look at a guy hang gliding, okay? And there's two objects on the ground. There's two objects on the ground, and they're in a green field, and he's trying to tell them apart. So we'll just use the green from the field. It says a hang glider is flying at an altitude of 120 meters. Okay, so his R now is equal to 120 meters. Okay, and it says here that two objects, and we're going to look at the green light wavelength, which is 500. The wavelength is going to equal 555 times 10 to the negative 9th meters. Okay, that's the wavelength that we're concerned about. His eyeball aperture is the diameter of the pilot's eye through the pupil is 2.5. D is equal to 2.5 times 10 to the negative 3 meters, because it's 2.5 millimeters. And it says, determine how far apart two objects must be on the ground if the pilot is to have any hope of distinguishing between them. Okay? All right, so what we have to do is we have to find S. In other words, we've got this big triangle here. Basically, this is 120 meters. He's up there about, that's about 350 feet. And we've got to find this difference S here, this distance S between these two. So it's just like our Hubble spacecraft, Hubble Telescope problem here. And basically all we've got to do is we got this theta min. All right? Well, we know this. The theta min is equal to S over 120. Okay? Because remember, when we were finding the arc length earlier, it's about equal to the arc length. Way back in Physics 1, we learned that S is equal to R times theta. Same thing here. This time we're just finding theta. So we've got to find S here is equal to R times theta. All right, but that theta min is equal to, what do we say is equal to? Like 1.22 times lambda over d, which would be S over 120 is equal to 1.22 times 555, yeah. Times 10 to the negative 9 meters divided by the distance. D was 2.5 times 10 to the negative 3. Okay? And so S, and you multiply all that by 120, and you come up with about 0.033 meters. Okay? So two things, that's not too bad. Two things that are two quarters that are about 2 centimeters, about an inch and a half apart. He can tell the difference between them. So that's not too bad. They don't look like one thing yet. Now an eagle, this is for a human. This is for a human. For an eagle, go through the same calculation, but the D for an eagle is about 6.2 times 10 to the negative 3 meters. That's his pupil, or her pupil, depending on if it's a male or female eagle. All right? And so if you just put this D back in here for this one, notice what you're doing is you're dividing by a number that's almost 3 times bigger. And so the S for an eagle, he can tell the difference at 0.013 meters. 0.013 meters. Okay? Now then, so that's what would happen. That's what happens with, so let's say they had an interesting little example problem in there. They talked about, let's say you're at the, at the Nelson Art Gallery, and you're looking at that tapestry of the water lilies by Monet, that they've got part of the tapestry of the water lilies there, and Monet was an impressionistic painter, and the way the impressionists painted. Y'all see Ferris Bueller? Remember Ferris Bueller? That was a. I don't think that was a Monet. That picture in the park. That's his buddy. I can't remember the other. I think it's a Surratt maybe, where they're all in the park there, and as his friend Cameron keeps staring closer and closer and closer until he's getting the different dots. He's actually staring at the different dots that it's made up of. Now, if you actually take a picture, if you went and took a picture of with a good camera at of the water lilies at the Nelson Art Gallery, you have to be careful because the aperture of the camera is much bigger than the pupil in your eye. So it will actually make the distinction between the dots that Monet used to paint the thing. So it'll kind of come out as a blob on your film, whereas with the image that's put on your brain, you can distinguish between the two. All right? Or you can't distinguish between the two, between all the dots, so that it looks like a coherent picture. Whereas the picture you took on the camera would be kind of fuzzy. Okay? All right. Let's talk about diffraction gradient. Now, one of the things that you can use for diffraction, one of the things they use is they use gratings. Okay? All right. Now, depending on how well machined, in other words, we're going to put a bunch of slits, a bunch of really small slits on a material, a reflecting type material, a mirror, a DVD. That's basically all it is a mirror with a bunch of slits in it. Now, how many slits, or round grooves actually? Now, how many slits does it have? What's the diffraction gradient that we can get? They can get up to 40, finally a good marker, 40,000 slits per centimeter. Whoa. That's a delicate machine doing something like that. 40,000 things per centimeter. That's pretty crazy. Okay? All right? So, hold on. Let me catch up with my notes here. I got way ahead of myself. So here we go. Oh, these aren't great. You'll be pleased to know these aren't notes. This is blank paper. We're almost done here for the most part. Okay. Now, do you ever do that in church? Count how many sheets of paper? Raise your hands. So he or she normally has 8. Okay, we're up to 6. Whew. Tommy's teeing off. Anyway, sorry. Okay, now, where was I? Diffraction gradient. Diffraction gradient. Okay? It's proved very useful in making CDs and things like that, and DVD players. How do they use it? Here's an example. All right? Example. Basically what, let me go to the picture so you can see. There we go. Just for a second, we'll run through this. I should have turned the film back on too. Whoa, I'd lose you. All right. Not that I haven't already. Okay. Is that flashing? No. No, of course not. There it goes. Okay. Liquid crystal display. We've kind of learned a little bit about that. Okay, here's an arrangement of diffraction gradient. This is coming through. And basically what it does is it can break light down into its different wavelengths. Works a little bit like a prism. Okay? Works a little bit like a prism. All right? So you get a diffraction pattern depending on the order, the different orders of intensity, M1, M2, okay? And basically, just through a double slit, the intensities are pretty close to the same. But in diffraction grading, you get more and more little bitty sub-intensities in here of different colors, and then certain colors really take off, all right? Now then, oh, by the way, here's the formula for the diffraction gradient. Sine theta equals m times the wavelength divided by d, where d is the difference between the slits, the distance between the slits. Now, think about that. If you've got 40,000 slits per centimeter, they're kind of packed in there, pretty tight, pretty darn tight, okay? So that difference in D. And then, so what happens is, you've all done this before, taking your CD and kind of turned it in the light, what happens? You see rainbow colors. This is what's going on, because it's a diffraction gradient, all right? It's basically what they've got. They've carved these grooves in there, and we'll get to how the CD works here in a minute. They've carved those grooves in there, and notice, a mixture of violet light and red light falls onto the grating. They're at different, since they got different wavelengths, their diffraction gradient, because the diffraction gradient again was this, sine theta equals m times lambda over d, which is the distance of the diffraction gradient. The different wavelengths are going to have different angles. So that's why they break them down into the colors. Working just like a prism. All right? So they wanted you for each wavelength to find the angle that locates the first order maximum. First order maximum is where m equals 1. All right? Well, that's not hard. If it's if you've got this, if it's 10,000 lines per centimeter, that's 10,000 lines per centimeter. That means you're going to have 1,000,000 lines per meter. So you got to flip that over. So they're 1/1,000,000th. They're 1 times 10 to the negative 6 separated apart, basically. What you do to find D, they'll give you this. You just flip that over. Just take the reciprocal of it. That'll give you D. Okay? But you got to be careful because they'll give it to you by centimeter. So you want to make sure that you add two things there, two numbers to that exponent. Add 2 to the exponent. All right. And so there you go. Wind up with this 24 and 41 degrees, so they came up with different numbers. All right. Wait a minute. I've been wrong. I'm always doing that. I'm always doing that. I always get frequencies and wavelengths flip-flopped. Violet light has greater frequency, shorter wavelength. Red light has a greater wavelength, less of a frequency. That is why it's to the left on that spectrum that we had. Okay, now, so here's how a compact disk works. Okay, here's how a compact disk works. Then, basically, they got this diffraction gradient, and they put all these pits and lanes in here. And basically, what they do is, as this thing goes around, they hit it with a laser beam. You all know, got that little laser beam in there that hits, and based on the thickness of these pits and the length of this pit, now sometimes this beam is half in and half off, and so you get destructive interference. Okay? You get destructive interference. And so for every time there's a destructive interference thing, they put a 1, code it with a 1 or a 0, and that's where you get that digital sound, as they talk about. It's coming from the digits, meaning 1s or 0s, coming based on, as this spins around, okay, then you won't have anything for a split second, all right, as it goes through this pit, and then at this end you're going to have some more constructive interference. So as depending upon how long the pit is and how thick it is, gives you the different code so that you get a sound, okay, that you just play back. All right, and they use that for, and they also use a diffraction gradient to get the beam a little more exact, okay. So the more expensive recording device or playing devices have those types of things. All right. Now then, don't even ask me how your iPod works. It's magic, okay? It's from the Apple Magic Land, where they just said, here it is. Actually, though, I know a little bit about it in that it's almost, we've gone back full circle to the old magnetic tape. And basically is that the iPod has magnetic storage. That the two guys who won the Nobel Prize like back in 2006 for all their work they did in '86 and '87 and for super resistomagnetic storage that they came up with, they're able to store bunches and bunches and bunches of information in a small area, and so it just reads the tape of that magnetic storage, which is exactly the way the old reel-to-reels used to work. So we've kind of gone full circle with the technology. Okay. It's still magic, all right? Getting 40,000 little grooves per centimeter. Give me a break, all right? I think they just make up these numbers. Who's going to, can we check it? No, we can't. Oh, well. That's what my sister claims when I tell her something fantastic about physics. She's like, you guys just make that up because nobody can verify it anyway. But no, it's true. I believe it. Okay. All right. So that's the way this works. Compact disk works. Okay, X-ray diffraction. Chemistry people, what do we have here? What is this guy? Did you all do your reading? Of course not. Okay, it's salt. Okay, it's NaCl, right? Isn't that what salt is? Sodium chloride, as I recall. There, that's all that I know. H2O and NaCl. That's the extent. Oh yeah, CO2. I do know that. And I know CO is bad. Like, yeah, carbon monoxide. That's bad. And I do know that when we burn fossil fuels, we're burning carbon, and so we release that into the air. That's why that's bad. Okay. But not as bad as the Reagan administration, who tried to say that trees were pollutants too, because they put carbon in the air. No, they eat carbon. Oh well. Anyway, so anyway, this is X-ray diffraction. Now, what happens with X-ray diffraction? Now, notice. The book makes some huge leaps and bounds here. They say, okay, let's assume the angle for this salt molecule that we have here. Let's assume that the angle theta here is is 30 degrees, so it's 0.5 between the things. And we're going to find the first dark fringe, and d, the distance between, is 1 times 10 to the negative 10th meters, which some of you, that's an old-timers, hardcore old physicists, they like this measurement. They call that an angstrom, right? Is that an angstrom, I think? Yeah. Call that an angstrom, which is basically the distance between atoms in a molecule. That's what they're talking about, okay? So, what is this wavelength then? As Emily and you guys can't see at all what I'm writing on the board here. So what is this wavelength? If we're just taking the first one and we let this be 0.5 equals 1 times lambda over 1 times 10 to the negative 10. Okay? When we do that, we get a wavelength that's very, very short, times 10 to the negative 9th, and that would be, that wavelength would be an X-ray. And so when they go through, so when you have X-rays, the diffraction pattern that they put looks like this. All right? And so you can shoot X-rays through different materials. This is what our material science guys do all the time downstairs. They shoot X-rays through different materials, and depending on the diffraction pattern that it gives you, you can go, oh, well, everybody knows that that's salt. Okay? This is just a Rorschach test. No, it's actually DNA. So they put the X-rays through the... Yeah. Very good. See? Eddie's physics. Optics. Good old optics. This is, I kind of wanted to just not really even talk about much of this stuff at all, but I just found it to be so apropos to our modern world, all this optics stuff. And I thought, because I will give it to you on Wednesday on your last test, I thought this would be a good time to go ahead and do one more thin film problem. Okay? This is the soap film problem that they've got on the last problem on chapter 11, or chapter 27. Oh, we're on chapter 27. This is chapter 27, and we will do the last concept and calculation, example 12. All right. So let's take a look at this problem, because you will see one like it on your take-home. Or not take-home. You're going to take it in class. All right. Basically what we have here is what they want us to do is, I've got soap. Here's soap. And soap's almost like water. It's got an N of 1.33. I got some glass down here, where N of glass is equal to 1.52. All right, and then I've got air. And the N of air is 1.00. All right? So that's what we've got. Now, it's coming in almost perpendicular. Here's our first boundary that we're going to worry about. See what the phase shift is here. And then we come down. Whoop, here's the second boundary that we're going to worry about. And we'll see if we have a phase shift there. Okay? Now, here's the way you do these thin film problems. You go, oh, okay. I know that the wave's got to go through this thickness 2 times. So you get 2t plus 1 plus 2. We're going to calculate our phase shifts. Equals, now, in this problem, listen to the way the problem is stated. It says a soap film is 375 nanometers thick. Oh, they gave us what the thickness of the soap film was. And coats a flat piece of glass. Thus, air is on one side of the film and glass is on the other side. Sunlight, whose wavelengths in a vacuum extend from 380 to 750 nanometers, So sunlight that goes from 380 to 750 nanometers is hitting on this thing, okay? Is striking this thing, not hitting on it. It's not asking for its number or anything. But it travels through the air and strikes the film nearly perpendicular. For which wave, and now the question is, for which wavelengths is this range, in this range, does constructive interference cause the film to look bright in reflected light? Okay, so we want to find, this is nanometers, okay? All right, now what we set this equal to, since it's constructive interference, constructive, we're going to set it equal to m equals lambda of the film, where m equals 1, 2, 3 on out. Okay? Because that's constructive interference. If it was destructive, what would we say? 1/2 lambda of the film, right? We'd say 1/2 if it was destructive. They want us to come up with constructive interference. Now, the physics part of this is figuring out what the phase difference is, or the phase shift is between for 1 and for boundary 2. Okay? This corresponds to 1, and this corresponds to 2. All right? So, now, since you've all have had this, all of 7 minutes of instruction in this stuff, you should know by now, and it was just 2 days ago, you should know by now that when light, even though I have to look it up every single time, when light goes from a lower index of refraction to a higher, is there a phase shift of 1/2 or is there no phase shift? There's a phase shift, right. As it goes from lower to higher, we have a phase shift of 1/2 lambda of the film. So far we've got 2t plus 1/2 lambda of the film plus. Now we've got to deal with 2. All right, so 2, it's going from 1.33 to 1.5, so it's going from lower to higher. So what does that equal? It's another 1/2 lambda of the film. And this equals either 1 lambda film, 2 lambda film, or 3 lambda film. Those types of things. Okay. All right. So here we go. Here we go. Oh, finish. All right, 1/2 plus 1/2. So we've got 2t plus lambda the film. And we just start pairing it up. All right, so if I subtract lambda the film from both sides, that's the way you do it. If I subtract this from both sides, subtract it from here, I get 0, or 1 lambda film, or 2 lambda film, on and on and on. All right, well, we don't want 0, so because we come up with 2t then equals, let's try 1 lambda of the film. Let's see if that works. Now, basically what we wind up with when we do this, by the way, they gave us t was equal to 353 nanometers. Do y'all remember what lambda of the film is, how you find that? Lambda in the vacuum over N of soap, which would be the substance. Right. Very good. Okay. And when you do that, when you do this first one, you wind up with lambda of the film, which is what we're after. We wind up with lambda of the film is equal to 2 times. Oh, let's do this. So let's replace that 2t with lambda in the vacuum, because that's what we're after, over 1.33. And when I come up with 2t times 1.33, I get something too big. I get a number that's outside, it's an X-ray. It's outside the realm of light. So I've got to go to my next guy, 2 lambda the film. Okay? Got to go to my next fringe, and then I wind up with something that's right around 499.
Why do you use lambda instead of like m lambda over d? Because I don't know, like the only one that I have is sine theta.
Oh, this is the thin film problem. This is thin film. We kind of went back to where we ended on Monday. All right. So that's how you do those problems. We won't have one where you got to find the range. I didn't finish it quite yet, but the rest of it's in your book. It's example 12. All right, I got one last thing to show you to kind of whet your appetite for relativity. Then I'll let you go. It's only about 4 or 5 minutes long. We'll turn out the lights completely so you can go completely asleep. Oh, shoot, why didn't I turn on the darn thing? Gosh, dang. This is a technical challenge for our AV crew back there. All right. If you ever kind of want to get your brain turned on, if you're sitting around going, wow, I'm bored and I want my brain to hurt, all right? One thing you can do on your computer, is that turned on? Yeah. Yeah, good. One thing you can do on your computer is you can go to this NOVA webpage, or I just like the, and go to this Elegant Universe. This is a book written by Brian Greene, who is a string theorist. And string theory, some physicists say it's not a theory, it's just a yarn. Physics humor, all right? All right, but anyway, because they haven't been able to, Einstein came up with some wild stuff, but it's all been verified in the lab, okay? And then that makes it science. Right now it's just, and that makes the theory of gravity is we've got a pretty good handle on it, sort of. We don't know what causes it. We have no idea why 2 bodies attract each other. We just know that they do. That's where some of the pioneering work is going on, and the string theorists think that maybe they've figured it out. But anyway, here we go. Let's just watch a few of these. Hopefully this will work. We're going to watch the 6-minute one, and then we're going to watch, no, let's just watch this 7-minute one. And then I'll let you go. Yeah, because 6 and, oh yeah, that'd be too late. And I've got an appointment. Oh.
Dimensions of space.
Let me get it bigger.
In a single fabric of space-time.
But this stuff is pretty cool. Oh, shoot. Yeah, it's cool. How do I get it big? Try that.
Einstein came to think of the 3 dimensions of space and the single dimension of time.
Oh, I guess
bound
it's big
together
enough.
in a single fabric of space-time. It was his hope that by understanding the geometry of this 4-dimensional fabric of space-time, that he could simply talk about things moving along surfaces in this space-time fabric.
Like the surface of a trampoline, this unified fabric is warped and stretched by heavy objects like planets and stars. And it's this warping or curving of space-time that creates what we feel as gravity.
A planet like the Earth is kept in orbit not because the sun reaches out and instantaneously grabs hold of it, as in Newton's theory, but simply because it follows curves in the spatial fabric caused by the sun's presence. So, with this new understanding of gravity, let's rerun the cosmic catastrophe. Let's see what happens now if the sun disappears. The gravitational disturbance that results will form a wave that travels across the spatial fabric in much the same way that a pebble dropped into a pond makes ripples that travel across the surface of the water. So we wouldn't feel a change in our orbit around the sun until this wave reached the Earth. What's more, Einstein calculated that these ripples of gravity travel at exactly the speed of light. And so, with this new approach, Einstein resolved the conflict with Newton over how fast gravity travels. And more than that, Einstein gave the world a new picture for what the force of gravity actually is. It's warps and curves in the fabric of space and time. Einstein called this new picture of gravity general relativity. And within a few short years, Albert Einstein became a household name.
Einstein was like a rock star in his day. He was one of the most widely known and recognizable figures alive. He and perhaps Charlie Chaplin were the reigning kings of the popular media.
People followed his work, and they were anticipating, because of this wonderful thing he had done with general relativity, this recasting the laws of gravity out of his head. There was the thought he could do it again, and people want to be in on that.
Despite all that he had achieved, Einstein wasn't satisfied.
He immediately set his sights on an even grander goal, the unification of his new picture of gravity with the only other force known at the time, electromagnetism.
Now, electromagnetism is a force that had itself been unified only a few decades earlier. In the mid-1800s, electricity and magnetism were sparking scientists' interest. These two forces seemed to share a curious relationship that inventors like Samuel Morse were taking advantage of in newfangled devices such as the telegraph. An electrical pulse sent through a telegraph wire to a magnet thousands of miles away produced the familiar dots and dashes of Morse code that allowed messages to be transmitted across the continent in a fraction of a second. Although the telegraph was a sensation, the fundamental science driving it remained something of a mystery. But to a Scottish scientist named James Clerk Maxwell, the relationship between electricity and magnetism was so obvious in nature that it demanded unification. If you've ever been on top of a mountain during a thunderstorm, you'll get the idea of how electricity and magnetism are closely related.
When a stream of electrically charged particles flows, like in a bolt of lightning, it creates a magnetic field, and you can see evidence of this
On a compass. Obsessed with this relationship, the Scot was determined to explain the connection between electricity and magnetism in the language of mathematics. Casting new light on the subject, Maxwell devised a set of 4 elegant mathematical equations that unified electricity and magnetism.
We did those. We just took the calculus out of them.
Called
Those are differentials. We just took the.
And like Isaac
The
Newton,
first one was Gauss's law.
Maxwell's unification took science a step closer to cracking the code of the universe.
That was really the remarkable thing, that these different phenomena were really connected in this way. And it's another example of diverse phenomena coming from a single underlying building block or a single underlying principle.
Imagine that everything you can think of which has to do with electricity and magnetism can all be written in 4 very simple equations. Isn't that incredible? Isn't that amazing? I call that elegant.
Einstein thought that this was one of the triumphant moments of all of physics and admired Maxwell hugely for what he had done.
About 50 years after Maxwell unified electricity and magnetism, Einstein was confident that if he could unify his new theory of gravity with Maxwell's electromagnetism, he'd be able to formulate a master equation that could describe everything, the entire universe.
Einstein clearly believes that the universe has an overall grand and beautiful pattern to the way that it works. And so to answer the question, why was he looking for the unification? I think the answer is simply that Einstein is one of those physicists who really wants to know the mind of God, which means the entire picture.
Okay, well, and now what we're going to do is special relativity where there's no acceleration, which he actually did first, and then he went on to the throwing in the gravity part. All right, we are done. We are done. We'll have one more lecture on relativity, and then we'll do take-home tests. Or not take-home, in class.